Alright, so here we are with part 3 of section 3.5, Implicit Differentiation. Our job in this problem is to find the equation of a tangent line to a curve at a point. Now I know how to do this because I've been doing this all semester long. To find the equation of a tangent line to a curve, I find the derivative, and then I plug in the point. The point gives me the slope of the tangent line. Then I use the slope of the tangent line and the x and y coordinates of the point to write that y minus y1 is equal to m times x minus x1 business, so that I can get the equation of a curve, its tangent line, at that point. But what makes this one complicated is this hot mess of a curve. So I have to take the derivative of that. So I have to do the derivative with respect to x of 3 times x squared plus y squared squared is equal to 100xy. Alright, let's just start. Left-hand side, I've got a function raised to a power, so that's chain rule. Right-hand side, I've got two variables multiplied together, so that's a product rule. So the left-hand side derivative, I'm going to have that 3 times 2 times the quantity x squared plus y squared to the first, and then multiplied by the derivative of the inside of those parentheses, which is going to be a 2x plus a 2y times dy dx. Then we run into an equal sign. Right hand side, we're going to have 100 times, derivative of the first is 1, times the second, which is going to be our dy dx, plus the first one, x. Whoops, I made a mistake there. That's the derivative of x times just plain old y, plus then x times the derivative of y, which would be our dy dx. Okay. Now at this point, I have two options. My options are either to solve this for dy dx, or, since the problem never really asked me what the derivative is, I could plug in the 3 for the x everywhere, the 1 for the y everywhere, and then just get rid of all those variables, make it all be numbers, and figure it out from there, and then solve for dy dx. I mean, either way, ultimately, I have to solve for dy dx. But if I could just plug in a bunch of numbers and not have to do all the rest of that, I'd prefer. So that's what I'm going to do. Okay. Out here in front, 3 times 2 is 6, times 3 squared plus 1 squared, times 2 times 3 plus 2 times 1 times dy dx is equal to 100 times 1 times 1 plus 3 times dy dx. 3 squared is 9. Working for the left over here. 3 squared is 9 plus 1 is 10. 6 times 10 is 60. So we're looking at 60 times 6 plus 2 times dy dx is equal to 100 plus 300 times dy dx. Okay. 6 times 60 is 360 plus 120 dy dx is equal to 100 plus 300 dy dx. Move the dy dx's. In this case, I'm going to move the dy dx to the right and the constants to the left. So that's going to give me 260 is equal to, what is that going to be? 300 minus 120 is what, 180? Dy dx, which then gives me my dy dx, my derivative, is equal to 260 divided by 180, which is 13/9 when simplified. Drop the zeros, 26, 18, 13, 9, half each of them, you're there. Okay? So 13/9 is what? Oh yeah. That's the slope of the tangent line to the curve, because the value of the derivative when we plugged in the 3 and the 1. And now that I know the value of the derivative, I can just use that point slope formula and say that y minus 1 is equal to 13/9 times x minus 3, which gives me y minus 1 is equal to 13 ninths x minus 39 ninths. Or maybe we should simplify that and say 13 ninths times 3 is what, 13 thirds? And then move this 1 to the right-hand side, and that would give us what? Y equals 13 ninths x plus 1, so minus 10 thirds. And there's the equation of my tangent line to my curve at a point. It wasn't too terrible, only 5.5 minutes to do that one problem. All right. Hopefully we'll get through this for the rest of this video. If not, there'll be a part 4. So what we're looking at here is logarithmic differentiation. All right, so I'm done showing examples of how to take derivatives of implicit. Now we're going to take a look at when someone might use implicit differentiation in either a situation where you have to, or you might modify the equation so that you can. All right, so logarithmic differentiation is a technique where you can use logarithms and the properties of logarithms as an aid in differentiating non-logarithmic functions. Right? For this to work, though, you have to know all of your properties of logarithms. So do you remember these properties of logarithms? Okay. The log of a product, x times y, can be rewritten as the log of the first multiplier and the log of the second multiplier, the log of x times plus the log of y. The log of division becomes subtraction, and when you have an exponent, that exponent can be pulled out in front and made into a multiple or multiplier, a coefficient essentially. Right? Keep in mind that these rules work in both directions. That means that if you had two logarithms being added together, you could rewrite it as a product, or if you had two being subtracted, it could be written as a quotient. So we will use them in both directions. All right, so here's our example for logarithmic differentiation. My job is to take the derivative of y equals x raised to the 2x. I absolutely cannot do that because there is no rule that I have for a function, an x, raised to a variable. I don't have a rule for that. If it was x to a number, like x to the n, I got a rule for that. If it was just a function raised to a number, I got a rule for that. That's chain rule. I can do that. But when I have a function, variable, raised to a variable, I can't do that. So what I'm going to have to do is I'm going to have to use a technique called logarithmic differentiation. So what I'm going to do is I'm going to take this and I'm going to take the log of both sides. Now, I'm going to use natural log. And the reason I'm using natural log is because when it comes to taking derivatives, I prefer to take the derivative of the natural log over any other base of logarithm because it's easier. And now I'm going to fix the offending issue because this exponent, because it is now sitting in a logarithm, can now be pulled out in front. And so then this becomes the natural log of y is equal to 2x multiplied by the natural log of x. And now I have an orange equation there that I can take the derivative of. Now I have to be careful though, because to take the derivative of this, I have to use implicit differentiation. Right? So starting on the left, implicit differentiation, the log, the natural log of y with respect to x, the variables don't match, so this is a chain rule situation. So this becomes 1 over y times dy dx is equal to, on the right-hand side, this is a product rule. So the derivative of the first one is going to be 2 times the second, the natural log of x, plus the first one, 2x, times the derivative of the second, or the natural log of x is 1 over x. Okay? At this point, I'm almost done. Right? Because I only have one term that has a dy dx in it, and I could do a little bit of cleaning up over here, algebraically. So I'm going to go ahead and do that. Left-hand side, I have 1 over y times dy dx. Right-hand side, I have 2 natural log x plus 2. X times 1 over x. They cancel, we just get 2. Now at this point, I'd be tempted to just multiply by y. And that would be correct. Multiply both sides of the equation by y to get rid of that. And that's going to give me then dy dx is equal to y times 2 natural log x plus 2. Now, that's not right. And here's what's wrong with it. The original function was handed to me explicitly. Dependent variable equals blah, 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 independent variable. And if the original function, the original equation was handed to me explicitly, I gotta write the final derivative explicitly. So I'm going to rewrite this line as dy dx is equal to x raised to the 2x times the natural log of x squared plus 2. Now you might be asking how that happened. Well, the y turned into x to the 2x because that statement tells me that y is the same thing as x raised to the 2x. And then using rules of exponents, work in that 2 right there go. 2 times the natural log of x becomes the natural log of x squared. And now I have a derivative, or the derivative, of y equals x raised to the 2x. So, logarithmic differentiation is a technique that one can use to take derivatives of things for which we have no rules by rewriting it using logarithms as something for which we do have rules. Okay? We can also use logarithmic differentiation to take the derivative of things that look like this. Now you might be looking at going, why does he have so much space? Because we're going to need it. Okay? All right, so here goes. I could take the derivative of this as it sits, but that is going to require a product rule and a chain rule in the numerator, a chain rule in the denominator, and a quotient rule all together. So I'm going to make the following argument, that I could use logarithmic differentiation and take this derivative easier, because by using logarithm rules, I can turn that equation into the natural log of y is equal to 3/4 times the natural log of x plus 1/2 times the natural log of x squared plus 1 minus 5 times the natural log of 3x plus 2. And now when I differentiate this with respect to x, I get 1 over y times dy dx, because of the chain rule of implicit differentiation on the left, is equal to 3/4 times 1 over x, natural log of x, 1 over x, plus 1/2 times 2x over x squared plus 1, chain rule on natural log of x squared plus 1, minus 5 times 3 over 3x plus 2. Then a little bit of cleaning up, I got 1 over y times dy dx is equal to 3 over 4x plus x over x squared plus 1, those 2's will cancel, minus 15 over 3x plus 2. Now it's not acceptable as it is because of this y over there, so I have to get rid of that term. So I'll multiply both sides by y, and I get dy dx is equal to x to the 3/4 times the square root of x squared plus 1 divided by 3x plus 2 to the 5th times 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. And there's my implicit differentiation trick for taking the derivative of something big and nasty and ugly. I use logarithms and then implicit differentiation because each of these derivatives right here weren't bad. They were pretty straightforward and easy to take. I just kept reusing the rule. Derivative with respect to x of the natural log of, wow, I left out my argument of my logarithm there on my rule. the natural log of u is equal to u prime over u. And just kept doing this again and again and again 3 times. And it was fast and easy. Right? Now, if you wanted to, you could, at this point, find a common denominator and combine that hot mess all back together. I don't see an advantage to doing that. So I'm just going to call it good right there. Okay? And that brings me to the end of section 3.5. So implicit differentiation.